Hello, everyone. I'm happy to be here, and I would like to special thank about the committee that invited me. First of all, I would like to offer my presentation outline. As a background, I'm going to offer a short review of my research background on nanofluid and nanofluid advantage or disadvantage, why we don't have any application at the moment with nanofluid, lack of principal research, point on accurate publication. As a part of my work, about 80% of my time I worked on nanofluid in the last 10 years. 15% on general heat transfer and 5% on my theory. Then I'm going to explain a bit more. On nanofluid in the last 10 years, I worked experimentally, numerically, and mathematical modeling on the stability, natural convection, forced convection, jet cooling, and emergency cooling. I established a nanofluid research laboratory at the University of Pretoria since 2010. Therefore, my point of view is on the heat transfer side. Nanofluids is a multidisciplinary research. This is very important. If we are going to make a group, we must have physics, we must have chemists. Just with one discipline, the work is not going to work very well. And my idea is that if there is a lack of knowledge, it means that we have research opportunity. Still, we have some papers that publishing nanofluid is not a good fluid for heat transfer. My point of view is that usually such that papers, what they say that is right just for those nodal points that they have. But we have a lot of area that nanofluid give advantage. That means such that paper usually their conclusion to me is not right. It means that if we have 4 points for nodal point that give us a disadvantage, we couldn't conclude for all nanofluid, even for that nanofluid at all. For example, if we have natural convection, we have a lot of natural convection that says that in the natural convection, then we don't have any heat transfer improvement. Yes, for 1%, 4%, 2%, up to 4%. Yes, but we work before 1%. It gives us a very good improvement. It means that if for 1%, 2%, 3%, and 4% of exact case, we couldn't receive any improvement, we couldn't conclude that for whole range. This is the case that I'm going to explain later. Therefore, for the advantage, we can make adjustable property, improving thermal conductivity, higher specific surface area, and in contrary of some of the paper, we have the evidence that reducing of the pumping power for achieving equivalent heat transfer. And still, it's not the disadvantage. Still, we have a stability issue. Because a stability issue, for example, for me, I am a mechanical engineer. It's not my job, but I have to do because of nobody else doing that. That's why we couldn't work on that very well. We need the help of the other discipline, and we invited them in our research group. For example, I'm going to offer one slide from a published paper that claiming the pumping power it's get for the pumping power will reduce for the same amount of heat transfer. We also work on transient flow. In the transient flow, we find that the heat transfer is going to be improved. But still, we have some problems. Because some of the researchers are asking that whenever we are working with the nanofluid, which parameters must be compared with the one that is without nanofluid. That's why still we have a lot of different ideas. Some of them says that, okay, Reynolds number is fine and Nusselt number, some says that no, for example. For me, maybe we can think about the energy. Then the amount of energy, because one of the point of view is the energy. That's why we can think about that for the same removing heat transfer, which of them can use less energy. This is one of, but I haven't seen that any paper they include the sonication energy as well. That's why if we are going to work on the energy, we must count the sonication energy as well, because we already use some energy for the sonication. Then one of the point of view is the energy. But a lot of cases that published, they are pointing on the viscosity. While the viscosity gets increased, then the pumping energy gets more, and it is the disadvantage of the nanofluid. But at least for the natural convection, we can see that it is one of our published paper that for 0.05%, then we have improvement. Then the paper that published that for 1%, 2%, 3%, and 4%, we get disadvantage. They are right. But the conclusion is wrong because of they can just decide about what they achieved, not for whole range. You can see that for the less than 1%, we have the, then here you can see that for the natural convection, then we don't have any pumping power. But here is not allowed because it is Fe2O3. But whenever we have a multi-wall, this is another published paper of us in 2017, and you can see that the heat transfer increasing by 45%. 45% is too much, and it's not a lot. The stability is not the issue for the 0.1%. Then you can see that I'm trying to say that if we have 1 point of improvement, we can claim that nanofluid has somewhere improvement of the heat transfer. But even if we have 1,000 points of negative heat transfer, we couldn't say in general nanofluid at all is not good. This is the case. A lot of application for the nanofluid we have these days. That's why everybody working on the nanofluid. I'm not going to talk about them. But we have good improvement on the solar energy concerning the economic, environment, and energy. But why we don't have any applicant or any product in the market and they says that it is nanofluid inside? Why? When we are talking about advantage or disadvantage, our point of view is very important. It can be optimum energy whenever our concern is just energy. It can be controlling of viscosity. If we have magnetic nanofluid, then we can control the viscosity. Sometimes getting smaller viscosity is not good. For example, if you have in the case of the high temperature, that the viscosity will go lower and lower. Sometimes you need to keep it in the range. That's why we can use the magnetic nanofluid and we can improve the viscosity for a specific case. That's why in the case of the controlling the viscosity is another case. Sometimes the size and weight is important, more important of the energy. For example, we are going to cool the engine of one airplane, the emergency cooling. That's why at that case, the weight is more important. That's why if we can reduce the size 20%, it's more important to use such a nanofluid. Sometimes we are thinking about the safety and health environment, and sometimes time is more important. For example, I talk about the case of the local accident, loss of coolant accident in a nuclear power plant. The same as what we had in the Japan recently. Then whenever we are working on the emergency cooling, then the amount of energy that we are using is not important. The size is important and the time important. That's why if I can remove the heat faster, it is safer for me for such a case. That's why I'm trying to say that it is very important, but unfortunately these days I can see that a lot of research is just thinking about publication. This is one of the problems of the nanofluid. Not nanofluid, in general it can be for all the discipline, but in the nanofluid, I will explain later. That is the case that what we are looking for, and based on what we are looking for, we can see that in somewhere we can find the advantage for the nanofluid. With this introduction, my question is that the number of the papers says that nanofluid is better than the base fluid is more than the number of papers that says that nanofluid doesn't have any advantage. But why we don't have any application, why we don't have any industrial application, why we couldn't find that somebody offering a device with the nanofluid, so that, okay, this is with the nanofluid and it's small. Do we need still more time? I think that from 1995 up to now is enough time. It's enough, it's really enough time to we find at least one application. Or our way to research on that is wrong. This is the case I'm trying to say, that the lack of principal research. We have the lack of principal research in nanofluid. The poison for the nanofluid is that somebody has a setup, he offered some paper on that, and said that, okay, the setup is there, let's we put nanofluid, what happened? This is not the research, real research. Yes, whenever we are going, then we need the principal research. Yes, we can publish that one, but if we are going to work in the nanofluid, then we can see that we must work, in my point of view, in the last 10 years, if we are going to improve nanofluid, then we must work more in the principal research. Then I'm going to explain. The starting point to me is that the properties of the nanofluid, stability of nanofluid, mathematical modeling for the nanoscale heat transfer, and health issue. They are the most important things that we couldn't have. Then if we couldn't solve them, then we couldn't make nanofluid while we are working. I'm very happy today that I'm here, because when 10 years ago we sent a paper to the conference, usually they said that they didn't know what to do with that one. Really. And sometimes they put it after a while in the session nano and macro. They somehow make it. After a while, for example, 5-6 years ago, then starting to make exact session as a nano heat transfer. Now we have a conference for nanofluid. This is very important. I leave my house Monday at 10 o'clock. I get here yesterday, Tuesday, at 3 o'clock, because for me, this conference is very important. I lost my suite between this flight. That's why usually I would like to wear my suite. And last night I go to buy, but I couldn't find a place that is open. I'm sorry. Okay, anyway, that's why the property, whenever we are sending to a lot of journals, I don't like to name, but at least one of them, for example, International Journal of Heat and Mass Transfer, you send that the property of nanofluid, you say that, no, we are working on the application. If I don't have the viscosity, I don't have the thermal conductivity, how I can use it in the heat transfer? This is important. That's why it is us as well. We have a lot of publications that they are not right in nanofluid. We have a lot of them. That's why I'm going to explain. That's why, as if we spend more time on them and correct them, then we have a better future for the nanofluid. While we are all of us, we are working in the nanofluid. That's why to work in the right properties is important. The stability is very important. If we couldn't find a stable nanofluid, I see that a lot of papers that say, okay, we put the nanofluid in the radiator of the car. Okay, then I will leave my car for 6 months. And what happened to that nanofluid? But they will publish it, but it's not applicable. I couldn't say that mustn't be published, but I'm trying to say that nanofluid needs the principal research as well. How we can make it stable for a longer time. This is important. But I don't think that it is hard, but we must find just right person and we must make it in our research group. And the mathematical modeling of nanoscale heat transfer, we have a lot of paper published with the commercial software, ANSYS, Association Plus, different. But have you seen the user manual, that which equation is working? We have at least 6 forces between the particles. And if we are working with the ANSYS, ANSYS is not working for the nanoscale. That's why we have to use user-defined function to insert the right equation. This is the case that, and also I'm going to explain it later. Also, is it right if we assume nanofluid as a homogeneous one-phase flow? If it is, and what is that, the Brownian velocity? In the homogeneous, we assume that both components, they have the same velocity, but in the nanofluid is not the same. That's why we have a lot of publication with the assumption of the homogeneous one-phase flow. And the other one is health issue. If you are going to use in the nanofluid for the nuclear power plant, is fine, because if the power plant crashed, then we don't think about the nanofluid. Still, we must think about the material, the nuclear material. But if you are going to use in the core, if the core crashed, what happened to that nanofluid? I went to another conference and somebody worked very well in the health issue and said that we are putting the gold and nanoparticle in the injecting and we improve the cancer. I asked him that what happened to the extra particle. He talked about the gold particle. I said that I don't know, but while he's better is fine. That's why we have a lot of questions in there. If we work in these principal cases, then we have improvement in the nanofluid. I'm not saying that we must just think about that, but it must be a part of our work. We must think about the stability, we must think about the properties, and we must think about the mathematical modeling. If we offered a right mathematical modeling for the 2-component flow, we no need to go follow the to find the properties, because it is two component. Whenever we are going to find the viscosity or thermal conductivity, that we are assuming there is one phase. That's why we are going to find the equivalent or effective thermal conductivity. But if we have a right equation for two component flow, we no need, because each of them has its own property. We no need to use the. For the experimental correlation, we have more than 50 equations, much more. I just write the safe because I count up to 50 and I get tired. We have more than 50 viscosity. We have more than 5 density, but one of them is us, and 5 specific heat capacity. Then you can multiply them together, which combination. If you are going to use equation, which combination you will choose? Then if we are going to just publish, then you can, for example, just joking that you can find that which of them is matched with the experimental, then it's easier to publish. But the thing is that it's very important that what we are, still I can see that somebody offering, we have just 5 equation for density. If we don't cite that 50, it doesn't matter. But if you are going to offer the density for the nanofluid, at least you must offer that 5. But I can see a lot of papers that trying to work in a new way, but they don't cite the previous work. Then it means, not the citation, it means that I am aware of that. That one is not working for me. And also we have a lot of equation that it's not equation, actually, it's a curve fit. That's why this is another case that they're offering curve fit instead of the equation, but they can publish. Parametric effect on the thermal conductivity, I know everybody knows, just as a review. The important one, volume fraction, property of the base fluid, property of the particles, temperature, particle size, pH, how is well homogeneous the dispersion, shape factor, nanolayer thickness, if there is a settling down problem. We don't have any hybrid equation that count all of them. And the nanolayer is very important. We find out that if your volume fraction is more than 1%, then the nanolayer is important. But we have a lot of applications that still using the mixture theory for more than 1%. That's why because while we are here, most of us, we are a reviewer as well. That's why if there is a paper in your hand, we must correct it. This is the place. I'm just offering some of the papers, some of the models. This is for the aluminum oxide. We change the volume fraction. Everything is the same, the size, everything. And we can find, you can see that each of them is different. And we can see that the Maxwell one. I don't know, but I think that about half of the papers that publishing, they are using still Maxwell equation for the thermal conductivity. Maxwell equation just count the volume fraction. It's not the size, but we know that the size is very important. But nobody asked. One paper was in my hand. It's from a very important university, and they work up to 5% with Maxwell. I said, no, I'm sorry, it's not working. Why? We have a lot of equation. Why you use Maxwell for 5%? I said, okay, in our lab, we see that is now no difference. I said, okay, it's not working like that, even if you are from one of the famous universities, but again, you must offer a reference, and it's not right. And you can see that when the the diameter change, about 20, most of them, the important one that I offer here, then can offer something the same. But the other one, you can see that when the dimension gets less. And also, some of the papers, they say that I found a lot of papers that sent me, even they forget to numerical one, they forget to write the size, because they don't need the size, but it is important. Some of the thermoconductivity nanofluid, I see in some paper, they say that the nanofluid can improve up to 300%. Even I am in the side of the positive side of the nanofluid, but I haven't seen 300%. That's why our data must be accurate as well. But we have different equations. Still, for the same nanofluid, somehow the same amount, but we can see that a lot of difference because we don't have any standard preparation of the nanofluid. We must somehow, I think that a lot of things must be changed in the universe, in the conferences, we're still working with 100 years ago. When I sent a paper that Big Bang doesn't work, I have the evidence, I have in my theory, after 12 years, but nobody even publishes this, but they don't say that is wrong. So, oh, sorry, it's not in our scope. But you can search on my name and Big Bang. In May, I offer after 12 years a theory that Big Bang is not working based on fluid dynamics, because the cosmologists, they don't know fluid dynamics, they don't know nature, they don't know pattern in nature, they don't know constructional law. That's why we must improve all of them together and offer it. And if something is wrong, we must say that. At least I sent to 6 journals, all of them said that it's not in our scope. But if you search on my name, and that's why from now on after, my time will split, because that 5% that I mentioned, that I'm working on the fluid dynamic from nanoscale to universe scale. That is still nanofluid is somehow inside, but in one side. Okay. That's why we can see that we have a different value, and I had this word, room temperature. I don't know, in my room temperature is something, in your room temperature is something, but we have a lot of paper published. They said that it was in room temperature. Okay, if it was in room temperature, then you had that something to say that your room temperature, it was which temperature. And also, if in general we are talking about room temperature will changing from 1 hour to the other one. It's not fixed. Then you must put one air conditioner in your lab and keep the temperature. And some temperature is not working like that. Then we have the same story for the viscosity. Just I would like to offer, this is the experimental, and this is some model with that experiment. That's why our data, usually if we fit it with some, our correlation, if we fit it with some data is working, but after that, if we check other data, sometimes is not working. Nanolayer that I explained, then whenever we work a lot on nanolayer, and we offered one thickness for nanolayer. This is important. That thickness can work everywhere. But I think that you can work on it and improve it. But it's very important that this thickness of equivalent thickness of the nanolayer, it's just depend on the size of the particle. I see in some papers they used a value for the thermal conductivity of the nanolayer, and they say that sometimes is equivalent to the base fluid. Anyway, the thickness of the nanolayer, we find that it can be it is this equation, but it is equivalent because it is not a gap. It means that from exact amount, we have a void there because it is, this one is the mixture theory, and this is the data for the experimental and for the evaluation of the model. In the case of the multiphase flow, then we have different models. Again, we must work in the principle that which model is working, and we have two components. And we must keep the forces. While we are a bit behind the time, then I would like to just offer the important part. The stability is very important. In some of the paper, but previously, more or less previously, they offered the term and they said that we take a look at the term and we find that it is stable. I don't know how to find. If they are fortune teller, I don't know. But whenever we are making the term, then we will put one drop of the nanofluid and we will dry it. Then the particle will goes on the top of each other. How we can find that from the picture of the dry nanofluid that was stable? That's why they stable. But to find the size is very important. If it is, then to find the size, we can use the term or same. But zeta size also usually, and the zeta potential and UV spectrophotometer, they can work, but usually while they send a beam of the light inside, and we don't have the transparent nanofluid usually, after 0.1 or less than 1%, then the zeta potential will go out of the range. It's not working. That's why but I have an idea for that. Usually, I provide that for the stability, we can start with the visual. Yes, the first point is visual. Because if it is visually stable, then we can go for the next. If it's visually is not stable, then we find it. And we can find one of the properties by the time. But that time at least must be five times of our experimental time. I contact a lot of, I'm talking about the last 10 years up to now, they send nanoparticle to you or nanofluid, it doesn't have any expiry date. But we find that it is, because if you keep the particle for a few years, after that you use it, the property of the active nanofluid is completely different than, at least for some of the nanofluid that we saw. Effect of the stabilizer we don't have. How we make the large amount of nanofluid? This is very important. That's why while we have not a lot of time, just I'm explaining that for the CFD simulation, if you find a paper in your hand, you must ask that why you choose this equation. You have more than 10,000 combination. Why you choose this one? We published one paper then showing that if you choose different equation, completely you can find different simulation. That's why the opportunity for the nanofluid at the moment, producing nanoparticle economically with expiry date, producing nanoparticles with more accurate size. A lot of time we will make a term and we say that it is a range of the particle. Completely is another story. Even we couldn't say that range, we can use the average for that. For the health and safety, is very important. We must find for each nanofluid at least one equation. And also, the other matter is that for all of the industrial application, we are not working with the 1 atmosphere, but almost all of the published paper on the properties of the nanofluid is for 1 atmosphere. That is important. That's why we couldn't. If I'm going to design with a nanofluid. I need the property. If I don't have the right property for that exact temperature, size, volume fraction, and pressure, the same for the effective viscosity, the energy density that we need for the sonication is very important. And I'm just explaining that one. And the nanolayer providing a standard way to make nanofluid, especially in two-step method. Research on the effect of the stabilizer on the nanofluid. Mathematical modeling for the two-component flow, nanoparticle and flow, and the health issue. The health issue, if the nanoparticle released in the area, it can attack skin, lungs, and eyes. We don't have any published paper that says that if the nanoparticle goes to the eyes of somebody, what happened? Where it goes? It depends on the particle size. That is important. If you are going to make an applicant, if you are going to put it in the radiator, if the car crashed, what happened to the skin? If it goes to the skin, go to the lung, or goes to the eyes. That's why it is multidisciplinary, and we need the other discipline to come and help us, and we can make a multidisciplinary research with them. Just if you give me 1 more minute, this is important, that some point of the accurate publication. We have two kinds of the publication, experimentally or numerically. For the experimentally, the preparation, volume, energy density is very important. I see a lot of paper, they refer to another paper. That's why I said that if you just skip the paper and publish it, then somebody else can refer to that one. In one paper, he said that I put sonication for half an hour for measurement. It was stable. For measurement, we usually make 50 to 100 milliliters. We will not make 2 liters for measurement of the thermoconductivity. Then if you put half an hour for 50 milliliter, the other one referred to this one. We use what he did, and they put, again, half an hour for 5 liters. It's not working at all, at all. And how they prepare it, because of we have the laboratory, if you use the nano sonication has exact energy density ultrasonication. That's why if you put the probe inside, the energy goes to up to exact place. And if you make it more sonication, someone said that, okay, it needs 2 hours, we put 1 day is better. It's not better. If it is bigger size, then after the sonication, make it homogeneous, then start breaking down the particle, bigger particle. It depends on that. That's why preparation, the temp size for the experimental, it's a need. It's a need. Then I'm going to show you that this one. The manufacturer, we bought it, claim it 100 nanometer, but you can see that it's more than, it's a 14 nanometer, it's more than 100. That's why for the experimental work, definitely if you are going to review it, you must ask the temp, it must be zeta potential, UV spectrophotometry, visually, or property, one of the property by time. Uncertainty analysis is very important, lack of data instead of innovation. I see that some of the reviewer these days is usual. It doesn't have innovative. I don't know what they mean with the lack of data. If we have a lack of data, it is a must to publish it. But innovation, yes, is important. But if we have a lack of data, then for the experimental one, then it can be. And conclusion must be limited to the achievement. If I work for exact amount, then I mustn't say that it is not working for full range. For the numerical one, then innovation and application is very important. I see a lot of people that they make one cavity, they put the source, at this point is one paper, and put that source on the other side. And with one idea, I see one PhD student, I don't like to say that which country or which university, but he told me that he published 24 ISI from his project, PhD project. It's not working like that. That's why, yes, if we are going to work with a numerical and we just would like to publish, point of view, if it is one component or two components, properties, it's very important that don't use the Maxwell for, I don't like at all, because, but again, while it's working for less than 1% is important, and if it is more than 1%, the Maxwell is not working, and non-linear is more important, and conclusion also must be limited to the achievement. That's why, in general, I feel that we have a lot of opportunity, research opportunity in the nanofluid, but still we need the principal research to make improvement. And I'm happy that now we have different nanofluid conferences at the moment. In order to improve the principal knowledge into the different aspects of nanofluid needs our attention in principal research. Thank you very much for your attention.